Alright, I just finished making this video and then realized that my mic was turned off for the entire time I was recording. So this is take two. Alright, so what we're talking about today, and the first kind of new thing we're going to be talking about this 6 weeks, are electron dot diagrams, or Lewis structures. And those names are kind of interchangeable and they get mixed up. You might hear them called Lewis dot diagrams or electron dot structures or whatever. They all mean the same thing. All right. And what they are is a way that we can use what we know about valence electrons to kind of make sense of how atoms are going to bond with one another. So just a quick reminder, valence electrons are the electrons in the outermost ring of an atom, so the ones furthest out in the farthest out shell from the nucleus. This is just an example of a Bohr model. You can see they've got the rings here. The first ring only holds 2, the second ring holds up to 8, and then the third ring holds up to 8 as well. In this case it only has 3 because their atom that they were modeling had 13 electrons total, so you end up with 3 valence electrons in the outermost shell. So if you're ever not sure about how many valence electrons something has, you can draw out your Bohr model to figure it out. That's the most foolproof way to do it. Alright, and to make your electron dot diagrams, they're pretty simple. All it is the symbol for the atom, so the letters off the periodic table, with dots around it to represent how many valence electrons there are. We don't care about how many total electrons there are, or how many protons or neutrons or anything like that. All we care about is the number of valence electrons they have. So here you can see they have all of the noble gases: helium, krypton, neon, xenon, argon, radon, all those guys that are on that far right column of the periodic table. And these all have 8 dots around them because they all have that full outer orbital with 8 valence electrons. Right, so you'll see when we do some other elements that they're going to have different patterns of dots because they have different numbers of valence electrons. Alright, and the reason these are useful is because we can use them to show how elements bond with one another. So here we've got water, H2O, and if we were going to draw each of these elements separately, we would say oxygen has 6 valence electrons. Alright, and we know that because we can go draw a Bohr model of it, or the quicker way is to just look on what row of the periodic table it's in, what column, and you can tell based off that if you're familiar with it. But if you're not sure, drawing a Bohr model always works. But for now, I'm just going to tell you all oxygen has 6 valence electrons. And when you fill them in, you go 1 in each compass direction. So north, south, west, east. And then you can start making pairs. You don't start immediately making pairs. You got to have 1 on each side first, and then you pair them up. So we've done that. That's 4. We need 2 more. So we'll put 1 here and 1 down here to make a pair on the top and the bottom. Alright, the hydrogens, on the other hand, hydrogens only have 1 electron, like total at all. So that's their only valence electron. It's just the one that they've got. Alright, and the thing is with these elements is that everybody wants to have a full outer shell. That's when they are the most stable. Is when they're in some kind of a compound where the bonds they're making allow them to have that full outer shell. So if they're in a situation like this, where oxygen has these 2 electrons that it wants to pair up and get up to 8, and the hydrogens have these 2 that they want to pair up and get up to their full outer shell, which would be 2, then they can share and form what's called a covalent bond. So if the hydrogen shares this electron with the oxygen, and the oxygen shares that one back with the hydrogen, same thing over here, they each share one of their electrons that's not part of a pair, you end up with what you've got on the screen here, where these ones here are being shared between both elements. Alright, and the way that's drawn is if you have a pair of electrons that's shared in a covalent bond, you draw it in as a line between the two atoms. So you draw your H for a hydrogen atom, then a line, then your oxygen atom, another line, and then your H for the other hydrogen. So these two lines represent a pair of shared electrons between each of those sets of atoms. The pairs up here that aren't bonding with anything, that are just belonging to the oxygen, stay drawn in as little pairs of dots. So the trick here is just remembering that each of these lines counts for 2 electrons in a bond. So if we go through and count now, we can count the electrons that our oxygen has. 2 from this bond, 2 from this bond, that's 4, 5, 6, 7, 8 total. It's got a full outer shell. Each of these hydrogens has the 1 bond, which gives them 2 total electrons, so they've got a full outer shell. Because remember, they're real small, they've only got that first inner shell as their valence electrons. So in this molecule we've drawn here, everyone's happy. This is what water looks like, H2O. Alright, it gets tricky because sometimes making 1 bond between the atoms isn't enough to make everyone happy. Sometimes they need to share more, and they can form double or even triple bonds occasionally. So if we were going to draw out CO2 like they've got here, they've got the carbon in the middle with a total of 4 valence electrons. Alright, and again, you know that from either drawing out your Bohr model or knowing what column of the periodic table it's in to know how many valence electrons it has. And then your oxygens each have 6. So we've got over here an oxygen, and when we fill in these dots, you got to remember 1 on each side before you start doubling up. Oop, see, I messed up there. Luckily it's easy to fix. I was just going too fast because I already knew what it looked like from the other one. Alright, so once we've got them set up like this, our oxygens only have 6 electrons, the carbon only has 4, they want to get more. So in order to do that, they're going to start sharing with each other. When they share electrons, if there's already a pair, it's never going to be those that are sharing. It's always going to be these ones that are on their own that are leaving to be shared. So here we'll say oxygen can give up this guy to go be shared with the carbon, and the carbon will share this one back in return. And same thing over here. Oxygen can share with that. The carbon will share that one. And if we rewrote this, it would look like this. Alright, instead of having these electrons here in the middle between the two, they've been turned into bonds and shared. And if we go and count now, our oxygen has 2, 4, 6, 7. Same thing over here, 2 from the bond, 4, 6, 7. And then our carbon has 2, 4, 5, 6. So we're getting closer, but we're not quite where we want to be, where everyone has a full outer shell of 8. So in order to make that happen, we just got to share again. So the oxygen has one little leftover guy down here that it can share, and the carbon can share that one back. And then same thing over here. The oxygen can share this guy with the carbon, and the carbon can share this one back with the oxygen in order to make double bonds. So here, carbon in the middle, double bonded to the oxygen on either side of it. And then the oxygens still have their lone pairs out here that didn't bond with anything. So now if we go and count, we've got 1, 2, 3, 4, and remember each of these lines is worth 2. So 6, 8 on the oxygen. Same thing over here, 1, 2, 3, 4, 6, 8 total. And then the carbon in the middle, if each line is worth 2, you've got 2, 4, 6, 8 total. So everyone's got 8 total electrons, full valence shells. They're all happy. This is what your electron dot diagram for CO2 would look like. All right, so you'll get a lot of practice on that, but it is something that you kind of just got to practice at until you figure it out. It'll click eventually. All right, so because this stuff requires drawing, it's not great to have you do it in a quiz in Canvas for your homework. So what we're going to do is I want you guys to each get a piece of paper, and your homework will be posted in the PowerPoint under the notes, and I'll copy and paste these slides as well into the actual homework assignment page. But what I want you to do is go through and draw all 10 of the Lewis dot diagrams or electron dot diagrams for these elements, and then all 10 of these compounds as well. So we'll do an example here. We'll look at phosphorus, which is number 3. So your first step in any of these is going to be figuring out how many valence electrons it has. So if we go ahead and go look at a periodic table, we can find phosphorus here. It's P. And we know that it has 15 total electrons. So if we wanted to, we could draw out the Bohr model. And let's do that for an example. So first ring can only hold 2. So we'll put those in. Second ring can hold up to 8. So that's 2, 3, 4, 5, 6, 7, 8. So that's 2, 3, 4, 5, 6, 7. I think I'm 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're good. That's a total of 10 right there. And we said we needed 15. So we need one more ring. And we're going to put our last 5 electrons out here on this ring, so that our number of valence electrons comes out to be 5. Right, and that's when you can go and start putting the dots around your symbol to make your electron dot diagram. So here, remember, 1 on each side before we start doubling up, and then we double up when we have to. So this would be your answer for the Lewis dot diagram of phosphorus. If you doubled up to start with and went like that, that would be wrong. You've got to do 1 on each side and then start doubling and making pairs. Alright, so that's how you're going to do the first 10. The next 10 are trickier because they're asking you to figure out how the bonds work in each of these. Alright, so we'll do 2 examples here. We'll do one of the simpler ones, and then we'll look at one of the more complicated ones. And it looks like actually H2O is in here, so you already had one of them done earlier if you need to go back and look at that. But let's look at, for a simple one, let's just do number 11. We'll look at CCl4. Alright, so the trick in these is that you want to count up the total number of valence electrons you have from all of your atoms. So if we've got a carbon, and if we drew the Bohr model out for that, carbon's right here. It's 6, so it has 6 total electrons. In the first row, first ring, it should have 2. In the second ring, we'll put the remainder, the other 4, for a total of 6. So carbon has 4 valence electrons. which means that its electron dot diagram would look something like that, right? For chlorine, chlorine's over here with 17. So if we were going to draw its Bohr model, there would be 2 in the inner ring, 2, 3, 4, 5, 6, 7, 8 in the second ring for 10 total so far. 3, 4, 5, 6, 7 in the third ring for a total of 17, like it shows here. Which means we have 7 valence electrons for chlorine. So we drew those in, we would go 1 on each side and then start making pairs. Alright, so we know what each of the individual atoms is going to look like. The trick is knowing what the compound altogether is going to look like. So if we know, based on our formula, if I can get back to it, that we have 1 carbon and 4 chlorines, this one actually turns out to be pretty simple. Carbon's got 4 of these lone electrons. Each one of our chlorines has 1 of them. So if they just make 1 bond with each chlorine to the carbon, it should end up being pretty satisfied, right? We would say the carbon in the middle with a shared pair of electrons between it and the 4 chlorines. And then you've got to remember to draw in all of your lone pair electrons out here that aren't part of the bonds as well. You can't leave those off. So y'all can see for each chlorine, we took this lone pair electron that we had and we shared it with the carbon, and then the carbon gave 1 of its electrons back to each chlorine. So it created a bond between each one and the carbon. So this right here would be your answer for number 11. Alright, so that one was relatively simple. A trickier one is going to be something like number 15, where you've got 3 different elements in there that you're worried about. And they're all going to have different numbers of valence electrons to work with. Excuse me, it's getting late. So for number 15, we have carbon, which we know from our previous example looks like this. It has 4 valence electrons. We have hydrogen, which if we look at the periodic table, it's way over here. It's only got the 1 proton and 1 electron. So it's just that, an H with 1 dot. And then we've got oxygens, which we know from the earlier stuff we've done have 6 valence electrons. And if you can't remember these off the top of your head, that's totally fine. You can always draw out your Bohr model to figure them out. I'm just trying to save a little time here for y'all. Alright, so the tricky thing here is we don't just have 1 of each of these. We've got a whole bunch. So we have a bunch of carbons, 3 of them. And 6 hydrogens. So how are we going to get all these to work together so that we can have everyone happy with full orbitals? Well, the trick to this is to go through and add up your total number of valence electrons that you've got whenever you get stuck. So here, if each carbon has 4, we've got 4, 8, 12. Right? We've got 1, 2, 3, 4, 5, 6 from the hydrogens. and then 6 from the oxygen. So overall we have 24 valence electrons. Alright, and then your next step is to take a guess and sketch out a design, or not a design, but a orientation for the molecule that you think is going to be correct. Generally, if you've got multiple carbons like this, they're all going to bond with each other and make a chain, and whatever else you have, like the oxygen or whatever, is going to be stuck on the end of that chain. That's how it usually looks. And hydrogens kind of just fill in the gaps. So if we say we're going to assume that's the case here, and we've got a carbon with a carbon with a carbon bonding together, and then bonded to the oxygen. Then that's what we'll start with. So far we've used 2, 4, 6 of our available electrons. And all that's left to do is to go in and kind of fill in the rest. Alright, your hydrogens need to be bonded with something. And what we do with those is we kind of just fill up the gaps. So if carbon wants 8 electrons total for each one, that's a total of 4 bonds. So over here, we're going to have hydrogen, hydrogen, hydrogen. This one's got 2 already, 1 to the carbon on either side of it, so it only needs 2 of them. And then here, we can put in 1 of our hydrogens, doesn't matter which side you put it on. And then we're up to 6, right? We've used 1, 2, 3, 4, 5, all 6 of our hydrogens. So in order to fill out the rest of these valence shells for the carbon and the oxygen, we've got to start drawing in lone pairs. And all we're doing here is just filling everybody up. We're not worried about how many we're using until we get everybody full up to 8, and then we'll go back and count. Alright, so now that everybody is full and has 8 valence electrons, we can go through and count how many we used total. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we needed 26 electrons for it to work like this. And we only had 24 to work with. So something's not right here. We can't randomly create 2 electrons out of thin air. When you end up in a situation like this, where your electrons do not match up, you don't have enough electrons to fill up all of the spaces that need to be filled up. This is where you start putting in double bonds. So what we can do is say, if instead of having a lone pair here and a lone pair here, if we got rid of those and instead put a double bond in, now each of these atoms still has 8 electrons bonded to it, but we've reduced the total number of electrons we're using by 2. So if we redrew this, and went back and counted again for each of these atoms. For our carbon here, we've got 2, 4, 6, 8, because it has 4 bonds and they're worth 2 each. Same thing on this one, 2, 4, 6, 8. Same thing on this guy, 2, 4, and then 2 with the oxygen, so 6, 8. And then our oxygen has 2, 4 from the bonds, and then 5, 6, 7, 8 from its lone pairs. And all together, if we go through and count, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which is what we were looking for. So this would be the correct solution. All right, and that's about as hard as they'll get. That's why I walked through this one. A lot of these other ones on here are going to be much easier than that. All right, so let's do one more real quick, and then I'll leave the other 7 of them to you guys. So we'll do number 18 as well, which is SO2. So if we go and we look at the periodic table, we know from the one we just did that oxygen generally, or normally, before we do anything to it, has 6 valence electrons. See, I did it again. I drew them in doing pairs first because I already knew what it was going to look like, but make sure you don't do that. Do as I say, not as I do, right? One on each side, and then start making pairs. That way you don't get tripped up. All right, and we've got 2 oxygens because it's SO2. That's what that little subscript means, is that there's 2 of them. I'll do it right this time. 1 on each side, and then make pairs. All right, and then sulfur. It's in the same column as oxygen, so it has the same number of valence electrons. That's the great thing about the periodic table and the way it's organized, is it makes things easier for you like that. So if oxygen had 6, sulfur is also going to have 6 because they're in the same column. So here we've got 6 plus 6 is 12 from our oxygens for our total number of valence electrons, plus 6 from the sulfur, so 18. So when we finish our drawing, we should only have 18 electrons showing. All right. And usually the idea is if you've got like the H2O that we talked about earlier, where there were 2 hydrogens and 1 oxygen, the oxygen was in the middle and the hydrogens were on either side. Same thing with the CO2 that we had our example from on the previous page, where you had the 1 carbon and the 2 oxygens. The 1 carbon is the one that's going to go in the middle. So here, on our SO2, if we have 1 sulfur and 2 oxygens, we're going to say the sulfur is the one in the middle, and we're going to have oxygens on either side of it, bonded to it. And then we just start going through and filling things in until everyone is full with 8 valence electrons each. So the oxygens each need 6 plus the bond for 8. The sulfur needs 4 electrons plus 2 bonds for 8, and that would make everyone happy. But we've got to go count and make sure we're not using too many electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So in order to make everyone happy like that, we would need 20 total electrons. Unfortunately, we only have 18. So just like we did up here, when we had not enough electrons, we're going to get rid of some of these lone pairs and turn them into a double bond instead. So the final version of this, the oxygen on the left side didn't change at all. It's still just a single bond. But the one on the right is double bonded, and it only has 4 lone electrons, and the sulfur only has 2, because we got rid of these ones on the bottom of each one. So then if we go through and count, this oxygen on the left has 2, 4, 6, 8, so it's happy. Our sulfur has 2, 4, 6, 8, so it's happy. And this oxygen, 2, 4, 6, 8, so it's happy. And all together we have 2, 4, 6, 8, 10, 12, 14, 16, 18 total valence electrons, which is what we were looking for. So that would be your answer. All right. So go ahead, try and finish the rest of them. You're making drawings like this for each one, and then you'll take a picture and submit it when you're finished through Canvas. If you have any questions or you get stuck, you're not sure if you need to make a double bond or if it should be lone pairs or whatever, let me know. I'll come help you out.